The winds dance with steel, Tacoma Narrows, and engineering's harshest lesson. In 1940, humanity held a steadfast belief that it had mastered steel and concrete, convinced that even nature's most formidable obstacles could be overcome through engineering marvels. In the state of Washington, the Tacoma Narrows Bridge, designed to connect the city of Tacoma with the Kitsap Peninsula, was meant to be the ultimate monument to this grand hubris and aesthetic ambition. However, just months after its grand opening, this slender, elegant ribbon of silver steel would twist like a snake in the wind and tear itself apart. It would go down in history as modern engineering's most shocking and heavily scrutinized lesson in what not to do. This is the epic and tragic story of how the invisible hands of the wind turned a steel giant into a plaything, the legend of Galloping Gertie. Part 1. The Price of Elegance and the Thinning of Steel. In the late 1930s, building a suspension bridge over the turbulent waters of the Tacoma Narrows was the region's greatest dream. The primary obstacle, however, was cost. Initially, the design called for a traditional, proven, open lattice truss system, a structural framework that allows wind to pass harmlessly through it. But this conventional design required massive budgets that the state simply did not have. Enter Leon Moisseiff, one of the most renowned and respected bridge engineers of the era. Moisseiff was a genius who had played key roles in designing the Manhattan Bridge in New York and the Golden Gate Bridge in San Francisco. To dramatically lower the budget, Moisseiff proposed a new, audacious, and highly aesthetic design: massive, solid steel plate girders. Moisseiff's design made the bridge incredibly slender and elegant. Its width was unprecedentedly narrow relative to its immense length. Unlike traditional open trusses, solid steel plates standing 8 feet 24 meters tall were installed along both sides of the roadway. Theoretically, these plates would provide the necessary vertical stiffness. On paper, Moisseiff's calculations were flawless. The bridge appeared more than capable of withstanding static loads and the sheer pushing force of the wind. But Moisseiff and the other brilliant engineers of his time failed to account for one crucial detail: wind is not just a static pushing force. It is a dynamic, living beast that creates complex, swirling vortices as it flows around objects. This oversight planted the seeds for a multi-million-dollar catastrophe. Part 2. The Birth of Galloping Gertie. As soon as construction began, the design's fatal flaw made itself known. In the spring of 1940, while the steel deck was still being attached to the suspender cables, even a mild breeze caused the massive structure to ripple and roll up and down. The movement was so pronounced that the ironworkers experienced severe seasickness while walking across the span, constantly sucking on lemons to settle their stomachs. Watching the bridge's relentless bouncing and bucking, the workers quickly gave it a nickname: Galloping Gertie. On July 1, 1940, the bridge opened to the public with great fanfare, marching bands, and ribbon-cutting ceremonies. But Gertie kept dancing. Not only was the Tacoma Narrows the third longest suspension bridge in the world, but it had also instantly become a massive amusement park ride. People drove from hundreds of miles away just to experience the thrill of crossing it, watching the roadway rise and fall several feet ahead of them, causing the cars in front to disappear over the crests and reappear moments later. The engineers were fully aware of the situation and deeply concerned. To stop the bridge's alarming undulations, they installed massive concrete tie-down cables to the riverbed and added hydraulic buffers. But the sheer force of nature quickly snapped and shattered every band-aid solution they applied. Fate was weaving its web. Gertie's up-and-down dance was only the beginning. Part 3, the invisible claws of aerodynamics, the scientific flaw. At that time, bridge engineers largely left the study of aerodynamic forces to airplane designers. The prevailing belief was that bridges only needed to withstand gravity and steady, static wind pressure. However, the solid, massive side panels of the Tacoma Narrows Bridge had begun to act exactly like an airplane wing in a wind tunnel. When the wind struck the side of the bridge, it was forced to flow over and under the solid steel plates. This flow created low-pressure, swirling pockets of air on the backside of the bridge, a phenomenon known as a Kármán vortex street. These alternating vortices pulled the bridge up and down in a rhythmic pattern. But the true catalyst for the disaster was a phenomenon called aeroelastic flutter. As the wind caused the bridge to tilt slightly, the angle at which the wind struck the structure changed. This new angle caught more wind, twisting the bridge further, which then snapped back due to the steel's elasticity, only to catch the wind again in the opposite direction. The system had entered a self-feeding, destructive loop of energy. The more the wind tried to twist the bridge like a snake, the more the bridge's own flexibility amplified that twisting. On the morning of November 7, the wind would finally find that fatal resonant frequency. Part 4, November 7, 1940. The dance of death begins. The weather over the Tacoma Narrows was harsh that Thursday morning. Wind speeds had reached a sustained 42 miles per hour, 68 km/h. Since early morning, the bridge had been performing its familiar vertical bounce. But around 10:30 a.m., something unprecedented and blood-curdling happened. Unable to withstand the mounting stress, a suspender cable on the north side of the bridge violently snapped. This sudden break completely destroyed the bridge's delicate equilibrium. Gertie's seemingly harmless up-and-down rippling instantly transformed into a savage, twisting torsional motion. The bridge was no longer just bouncing, it was twisting violently from left to right, as if trying to fold itself in half. While one side of the 39-foot-wide steel roadway surged 28 feet into the air, the other side plunged 28 feet downward. The massive structure corkscrewed at terrifying 45-degree angles. It had become a colossal steel serpent thrashing in the gale. Toll guards and state police rushed to the scene, immediately closing the bridge to all traffic. But caught in the middle of the thrashing span were two vehicles. Part V, trapped on the steel snake. One of the vehicles was a delivery truck. Its driver managed to throw open his door, scramble out, and sprint backward off the bridge to safety. The other car belonged to Leonard Coatsworth, an editor for the Tacoma News-Tribune. As Coatsworth reached the center of the span, he felt the roadway tilt uncontrollably to the right and left. He lost control of his car, which slammed against the steel curbs. The angle of the road was so extreme that Coatsworth had to cling desperately to the door handles just to keep from being thrown out of the vehicle. Inside the car, barking in absolute terror, was his daughter's three-legged cocker spaniel, Tubby. Coatsworth later described those harrowing moments. Around me, I could hear concrete cracking. I thought the bridge was breaking up and my number was up. The car was sliding from side to side. I decided to abandon it. I opened the door and jumped. I fell flat on my face. The roadway was tilting at such an angle that I couldn't stand up. I crawled on my hands and knees most of the way, my breath coming in gasps, my knees raw and bleeding. Coatsworth managed to crawl his way back to the safety of the toll plaza, but his mind was on Tubby, the dog he had been forced to leave behind in the car. Meanwhile, Professor F.B. Farquharson of the University of Washington, who had been tasked with studying the bridge's movements, ventured onto the span with a camera. Farquharson captured the legendary, terrifying footage of the bridge twisting like a piece of rubber. Braving the violent motions, the professor staggered toward Coatsworth's car to rescue the dog. He reached the vehicle and opened the door, but the terrified Tubby bit the professor's finger. The bridge was now on the absolute brink of disintegration, and Farquharson had to retreat immediately to save his own life. Tubby the dog would be the only casualty of the Tacoma Narrows disaster. Part VI, the inevitable end and the scream of steel. As the clock neared 11:30 a.m., the sheer forces of nature finally overcame the molecular resistance of the steel. A spine-chilling sound of tearing metal erupted from the massive girders that had been violently wrenching back and forth for over an hour. The vertical suspender cables began to snap one by one, sounding like sharp rifle fire. With every snapped cable, the weight in the center of the bridge became more unbalanced. At 11:10 a.m., the catastrophe reached its climax. With a deafening roar, a massive 600-foot, 180-meter section of the concrete and steel center span tore away from the main cables. Twisting through the air, it plummeted 190 feet into the freezing waters of the Puget Sound below, erupting in a colossal explosion of white foam. With the immense weight of the center span suddenly removed, the tension in the main cables snapped back with unimaginable ferocity, violently whipping the massive steel towers backward. The resulting whiplash shattered the remaining deck sections, sending them plunging into the depths one after another. In a matter of minutes, a multi-million-dollar, state-of-the-art engineering marvel was utterly annihilated by a mere 42 mph wind. All that remained were the severed cables hanging mournfully from the giant steel towers on either side of the Narrows. Part 7. Lessons from the Rubble, Rewriting Engineering Books. The collapse of the Tacoma Narrows Bridge sent shockwaves around the globe. What stunned the world was not that a bridge had fallen, but that it hadn't been destroyed by a hurricane or a bomb. It was destroyed by its own aerodynamic design flaw. A high-level investigative committee of the era's top engineers and scientists was formed. The disaster effectively ended Leon Moisseiff's illustrious career. Just 3 years later, Moisseiff died of a heart attack. Many attribute his early death to the profound stress and heartbreak caused by the collapse of his masterpiece. Yet, the death of Galloping Gertie heralded an invaluable rebirth for modern engineering. 1. The birth of bridge aerodynamics. The Tacoma Narrows disaster permanently merged civil engineering with aeronautical engineering. From that day forward, rigorous wind tunnel testing became a legal and scientific requirement for every major suspension bridge built anywhere in the world. 2. The return of the open truss. Because the disaster tragically proved that solid plate girders act like sails blocking the wind, engineers returned to the open truss designs that allow wind to pass right through the deck. The triangular steel frameworks you see beneath modern suspension bridges exist largely to appease the swaying ghost of Tacoma. 3. The ultimate textbook example. Today, no matter where in the world you study physics or civil engineering, when you reach the chapters on resonance, aeroelastic flutter, or the Kármán vortex street, the very first thing your professor will show you is Professor Farquharson's black and white footage of a steel bridge twisting like a snake. In 1950, a new Tacoma Narrows Bridge was built on the very same spot this time, equipped with deep, sturdy, wind-permeable open trusses. Nicknamed Sturdy Gertie, that bridge still stands proudly today. The Tacoma Narrows disaster continues to whisper a timeless warning to engineers and humanity alike. Never underestimate the raw power of nature. Never let aesthetic elegance compromise structural safety. And never assume that mastering one branch of science allows you to safely ignore the others. The twisted steel wreckage lying at the bottom of the Puget Sound is not just a pile of rusted metal, it is the world's greatest sunken monument to the end of hubris and the painful acquisition of invaluable knowledge.